Okay, welcome back. Good morning. Welcome to session number 2 on side channels. The first presentation is going to be presented by Jean-Sébastien, and he will speak about the formal verification of side channel countermeasures via elementary circuit transformations. Thank you.
So thank you. So my talk is about formal verification of side channel countermeasures. So we all know that without countermeasures, it's very easy to extract the secret keys from a device just by measuring the power consumption. So it's a very powerful attack. So the most powerful attack is probably the classical differential power analysis, in which we make some key hypothesis on some part of the key, and then so we can predict, for example, using this key hypothesis, the output bit of some S box, and then we can classify the power traces according to this output bit. And if the prediction is correct, then we are going to, by subtraction, we obtain a differential trace with some peaks, and so we can quickly extract the secret key. So we need some countermeasures, and the most famous countermeasure is the masking countermeasure, in which instead of manipulating the variables in clear, we mask the variables with some random R. So instead of manipulating X, we manipulate X prime equals X or R, where R is random. So R is a random, so now X prime is a random, and so the power consumption becomes random, and so we don't leak information about the original variable X. So how do we compute with X prime equals X XOR R instead of X? So for linear operations, this is easy because, for example, for mixed columns in AES, because when f is linear, f of x prime is equal to f of x XOR f of r. So we can compute those two terms, f of x prime and f of r separately, and now f of x is masked with f of r. So that's easy for linear operations, and for S boxes, the most famous countermeasure is the classical randomized table countermeasure. But of course there are second order attacks in which we can combine the leakage from 2 points. So for example, the leakage from x prime and the leakage from r, and the combination will leak information about the original variable x. So such second order attack is more complex, it requires more curves, but this is feasible. So the natural solution to be secure against second order attacks is to use more shares. So we are going to use n shares instead of 2. So the variable x is shared among these n shares xi's. And the property that we want to ensure is that any subset of n-1 of these shares should be uniformly and independently distributed. So that if the adversary probes at most n-1 of these shares, or combines the leakage of at most n-1 of these shares, then the adversary learns nothing. So the countermeasure will be secure against a DPA attack of order n-1. So for linear operations, this is still easy, of course, because we can compute the f of xi separately, and know the value f of x is shared among the f of xi's. But for the S boxes, this is a bit more complex. So the problem is the following. We have the input shares, which are the xi's, and we must compute the output shares yi's, such that the XOR of the yi's gives S of x. And we must do this computation without leaking information about x. So in general, the countermeasures to do these operations are more complex, And also the proof of security. When there is a proof of security, the proof is more complex, so we may ask, but actually is the security proof correct? So in this talk, my goal is to describe a very simple formal verification tool to automatically verify the security of high-order countermeasure, high-order masking countermeasure, and the tool will be based on the common Lisp language, which is very well suited to perform formal manipulations. So usually to protect this box or a circuit, so Ishai, Sai, and Wagner showed a technique to protect any circuit against an attacker who can probe T probes in the circuit. So they showed how to transform any Boolean circuit into a bigger circuit that is resistant against an adversary who can probe T wires in the circuit. So in principle, we could write our S-box as a Boolean circuit and then apply the ISW transform, but this will be inefficient. So for software implementations, it is more efficient to use the Leuven proof countermeasure from Chess 2010. Because for example for AES, we can write the AES S-box as x to 254. And so this can be implemented as a sequence of multiplications over the finite field GF228. And then every multiplication can be protected using the same technique as in the ISW paper. So when we want to multiply x times y, where x is represented with the shares xi's, and we have the shares yi's. So we have to compute this product. So what we do is we compute all the cross products, xi's times yj, and then we recombine these cross products using some randomization. And one can prove that this countermeasure will be secure against an attack of order T, in which we probe T wires, if the number of shares n is greater than T plus 1. And for this, we also need some additional mask refreshing. So now we would like to formally verify such countermeasure or any other countermeasure based on masking. So this formal verification of masking has been initiated by Bart, Belaid, and Dupressoir and others 3 years ago. And Gilles is going to give the invited talk this afternoon on verification. And so in this paper they describe some automated method to prove security against a thief-order attack. And the technique only works for small values of T because the complexity is exponentiality in T. And this is exponential because we must verify the security for any subset of T probes, and there is an exponential number of such subsets. So the complexity is exponential, and so this technique is implemented in the EasyCrypt framework. So here, so today, in this talk, my goal is to describe a simpler technique to formally verify the security of the masking countermeasure. So at the beginning, it's essentially the same approach as in their paper, but I'm going to explain that it is actually simpler thanks to the common Lisp language, which is very well suited to formal manipulations. And then, since the approach is more lightweight, it was possible to extend the model to arithmetic masking. And the goal was to have a formal verification of some Boolean to arithmetic conversion algorithms. And also, in this talk, I will explain that for some simple circuits, it's possible to have a polynomial time verification instead of exponential time, and including for the Leuven proof countermeasure. So now I'm going to explain how to represent the circuit that we want to formally verify. So I'm going to consider a very simple circuit which is simply a mask refreshing circuit. So we start from n shares xi's, and at each step we XOR a random to, at the beginning, the first share and the last share, and then we continue, we XOR R2 to the second share and the last share, until the last but one share. So at every step we XOR the same random to two shares, so the XOR of the xi's remains the same. So the XOR of the yi's is the same as the XOR of the xi's. So it's just a mask refreshing. And so how do we represent this circuit? So we are going to use a nested list representation with a prefix notation. So for example, we can implement this kind of function in Common Lisp, which takes as input a list of shares. So for example, here for 3 shares x1, x2, x3, and it outputs the list of output variables. So here, this is the first variable, it corresponds to the first variable y1, because y1 is x1 XOR R1. So here we have plus, so I use plus for XOR. So it's plus R1 and x1, so x1 XOR R1. For the second variable, it's x2 XOR R2, and for the last variable, we accumulate the randoms, so it's the XOR of x3 and R1 XOR with R2. So we have this nested list representation, which is relatively lightweight. And now, assume that we want to verify some formal security property of this circuit. So I'm going to consider a very simple property, which is the following. If we look at the output of the mask refreshing, and we consider only a subset of the output variables, we consider a subset of n-1 output shares, then these output shares are uniformly and independently distributed. So we don't probe inside the refresh mask, the internal variables, we only look at the output shares, and if we have n-1 output shares, then they are uniformly and independently distributed. So of course this property is very easy to prove on paper, but to illustrate the approach, I wanted to perform a formal verification. So for example, assume that we want to formally verify this for n equals 3. So for example, we are going to consider the first variable, which is plus x1 and r1, and the last variable, plus x3, r1, plus r2. So we want to verify that these two variables are uniformly and independently distributed. So here we first note that the random R2 is used only once. So it can play the role of a one-time pad. And so the distribution of plus R1, x3 plus R2 is the same as the distribution of R2. So we can replace, we can perform a substitution. We replace this second variable by simply R2. So here we start from these two output variables, and we replace this second one by only R2. And then we can continue because we see that here the random R1 is used only once. So we can replace this first variable by R1. So eventually we have obtained a list of two randoms. So this shows that actually these two output variables are uniformly and independently distributed as required. And actually, if we work with Common Lisp, it's very easy to perform these elementary substitutions. We simply have to list all the randoms that are used, and if a random has been used only once, then it can play the role of a one-time pad, and we can make the substitution. So it's only a few lines of Common Lisp. So now if we want to formally verify the previous lemma, we have to consider all possible subsets of n-1 output shares. So there are n such subsets, and then for every such subset, we check that after a series of elementary substitutions, we get a list of n-1 distinct variables. And then this will show that these n-1 output shares are uniformly and independently distributed. So it's very easy to do this automatically, to write a function that does this verification. And so, for example, for n equals 3, we have this input, we have this output, and the function is going to consider all possible 3 cases and check that after a series of substitutions, we always get at the end a pair of distinct randoms. And so this proves, basically proves the lemma for n equals 3, and then we can do this verification for any value of n. So of course we would like to do some formal verification for more complex properties. So for example, we would like to verify the security of the Leuven proof countermeasure. So the basic algorithm in Leuven proof is this secure multiplication between A and B with the shares AIs and BIs. So for example, if we work with 3 shares, we have this representation. Here we have the 3 output variables. And here we recognize the cross products, A1, B1, A2, B2, A1, B2, and so on, and also the randoms for the recombination. So to verify the security of Leuven proof, we want to show that the adversary learns nothing from any subset of n-1 intermediate variables. So if the adversary probes any of these intermediate variables, but at most n-1 of them, then he learns essentially nothing. And this is based on the simulation framework from the ISW paper. So the simulation framework works as follows. So the adversary has n-1 probes inside the block cipher, and we want to prove that it's always possible to perfectly simulate these n-1 probes from a subset of the shares of the secret key. So initially we assume that we receive n shares of the secret key, and we want to show that for any subset of n-1 probes, it's possible to perfectly simulate those probes using at most n-1 of these shares. And now we can assume that these n-1 shares here are uniformly and independently distributed. So this means that it's possible to perform this simulation without knowing the secret key. So the attacker could perform this simulation by himself. So this means without knowing the secret key. So this means that he learns nothing from the n-1 probes. So this is the simulation framework. So now we want to perform this formal verification. So this verification formally. So I come back to for example, the representation of the circuit for n equals 3. So to formally verify the security of Leuven proof, we have to consider all possible subset of probes with n-1 probes. And then, as previously, we are going to verify that after a series of elementary substitutions, then it's possible, and applying the one-time pad rule, it's possible to simulate the intermediate variables using at most n-1 of the inputs. And so we have to do this verification for all possible set of probes. And again, this verification is very easy to implement. It takes only a few lines of common Lisp. So for example, here, if I consider, for example, the 2 output variables of the Leuven proof, here this is the first output variable and the second output variable. Here we see that the random R3 is used only once, so it is a one-time pad, so we can replace the second variable by R3. And here we see that R2 is used only once, so we can replace by R2. So we have to perform this verification for all possible subsets of intermediate variables. So it takes exponential time, so we can only do this for small values of n. So here is the timing of formal verification. So this is for Leuven proof, and now I'm going to describe an extension of this to arithmetic masking. So the goal is to formally verify a conversion algorithm from Boolean to arithmetic masking. So we take as input n shares, n Boolean shares, and we want to output the DIs, the arithmetic shares DIs, whose sum, arithmetic sum, must be equal to x. And actually, at last chess, at chess 17, and also this year, some very efficient high-order conversion algorithms have been published, and with the complexity independent of k, of the register size k. And this can be seen as an extension of the Goubin countermeasure, which was secure at first order only. But the proof is more complex, so we would like to have a formal verification of this proof. But the formal verification will be a bit more complex because we must handle both Boolean operations and arithmetic operations. So the algorithm, the conversion algorithm, is based on the fact that this function, this psi function, is affine with respect to the second input. It is affine with respect to R. So here in my circuit representation, I'm going to use this psi function. So here, this is an example. We take as input two shares here, two Boolean shares, and here we obtain the two arithmetic shares using the psi function. But now, since the psi function is affine with respect to the second variable, we can actually apply, we can use this as a simplification rule. Every time we see the XOR of two psi functions with the same first variable, we can replace this XOR by x XOR the psi of x and the y XOR z. So, and it's very easy to implement this in Common Lisp. We simply, when we see such pattern here with the XOR of two psi function, we replace this with the sum of x and the psi of the XOR. So to have the formal verification, we have a sequence of rules. We have 6 rules, and eventually we obtain the following verification time. So it takes a lot of time to verify the security, even for small values of n, because the complexity is exponential in n. So the main drawback of this approach is that verification is exponential time, because we have exponentially many set of probes to verify. But in the paper, I describe, but the advantage is that it's generic, because it works for any circuit. But in the paper, I describe also a technique to have formal verification in polynomial time, but only for specific circuits. It's not generic anymore. And the technique is to perform a sequence of elementary circuit transforms until the circuit becomes so simple that it's straightforward to verify the security property. And so in the paper, I describe a polynomial time formal verification of Leuven proof, and also of the multiplication-based mask refreshing. So in summary, I have described a technique to formally verify the masking countermeasure. So it is based on list substitutions, and it's implemented in Common Lisp, which is very well suited. So it's an extension of BBD15. So initially it's almost it's very similar to BBD15, but since the approach is more lightweight, it was possible to extend BBD15 to Boolean to arithmetic conversion. So the technique is generic, but in that case it has exponential complexity, but it's also possible to adapt the technique and obtain polynomial time complexity for specific circuits. So here I will argue that the main advantage is the simplicity, and most of the masking countermeasures can be verified with only a few lines of Common Lisp. And so I have put the source code of all the formal verification on GitHub. So thank you for your attention. Thank you.
So we have time for 1 or 2 short questions. question? So, in the way you present intermediate values and so on, you have many parentheses. So that means that the order of the execution of these operations is important, right? Yeah. So this applies mainly to software.
Yes. So for example, so for example, for event proof, yes, it applies in software. Yeah.
Other questions? No? Okay, then in the interest of time, we'll move on. Thank you again. We'll move on to the second presentation. We set up. Second presentation in this session is about drive-by key extraction cache attacks from portable code, and the presentation will be given by Leuven. Please.
Thank you for the introduction. My name is Leuven, and the title of my talk is Drive-by key extraction cache attacks from portable code. This is a joint work with Daniel Genkin, Oran Trommel, and Yuval Yaron. Cache-based extraction attacks have been known for a while. It has been shown that when an attacker and a target share the same hardware and the same CPU, the attacker can steal cryptographic keys using the shared cache between them. It can be done despite the confinement provided by the operating system and the virtual machine. However, those attacks assume that the attacker can execute native code on the same hardware that the target is executing. And while this assumption makes sense when we talk about cloud computing, or a device shared by multiple users, it's very unlikely that the end user would download an unknown binary from unknown source and execute it on its own machine. And indeed, we see that there are more and more applications that can be executed inside the sandbox environment of the browser, where the sandbox, when the same origin policy is enforced and the application itself is written in high-level interpreted language. On top of that, we see a rising trend of lockdown browser-only platforms, such as Google Chromebook, where the web browser is the only user interface, and even the administrator cannot execute native applications. Those limitations create new challenges for launching cache sidechain attacks from the browser. So first, when the application itself is written in high-level language, it's interpreted by the target's browser on its own machine, which results in unpredictable memory layout. Next, modern browsers provide isolation between different applications, so there is no shared memory between the attacker and the target. When it comes to writing the attacker code in portable high-level language, it introduces all kinds of overheads, including slower memory accesses, lack of access to CPU instructions providing accurate time source, and lastly, the inability to use dedicated instructions to flush the CPU cache pipeline and the cache itself. Despite all those limitations, we were able to extract cryptographic keys using websites. We implemented our attack using Google's portable native client and WebAssembly. We tested our attack on Elliptic's implementation of Curve 2519, Google's end-to-end encryption library, and OpenPGP.js as well. We tested our attack on Google's Chromebook, as well as on a regular laptop, where the attacking code was running inside Firefox, and the target code was running in Chrome. A specific attacking scenario we investigated was a user receiving an encrypted email, then using Google's end-to-end extension to decrypt the email. But before receiving the email, he was watching a movie using an online streaming service. And when he clicked play to see the movie, a pop-under advertisement opened up in the background. We demonstrated that the attacker code can be embedded in the advertisement and extract cryptographic keys. To understand how this attack works, we have to understand how to monitor the cache from the browser. So first of all, modern CPUs has multiple levels of cache. And we focus on the CPU's last level cache, which is shared between all the processes running on the same CPU. The CPU cache is divided into multiple cache sets, and each memory block can be mapped to a specific CPU cache set when it's accessed. To monitor the cache, we have to construct eviction sets. Each eviction set consists of a set of objects mapped to the same CPU cache set. This will allow us to induce contentions to the CPU cache and extract fine-grained data. So to construct those eviction sets, we have to recover the mapping between portable environment objects and the CPU cache set number. And while the portable environment address space has only 32 bits, the cache set number is derived from the physical address space with 64 bits. And this translation is not direct. First, the portable environment address space is translated by the browser to the virtual address space, which is divided into two parts, page offset and page number. Then, it's translated by the operating system to the physical address space, from which we derive the cache set number. The only part consistent between all those mappings is the part that corresponds to the page offset, namely the 12 least significant bits. So from this diagram, we can see that the portable environment address space has the 6 least significant bits, but we have to derive a method to recover the 5 most significant bits. So past approaches to solve this problem used huge pages. Huge pages extend the page offset from 12 to 20 bits and reveal the entire cache set number. However, huge pages are not available to the portable environment. It's a feature that only native code can use, so it's not applicable to our case. Another approach is to use large cache sets. The main idea behind this approach is to use the 6 known bits and treat all the cache sets that share those bits as one big cache set. It introduces a factor of 32 slowdown, but it's sufficient to randomize the kernel ASLR. However, it's too coarse to extract cryptographic keys. We extend the technique of Liu et al. And use the known 6 bits, as well as few new tricks described in the paper. The main idea of this approach is first, we allocate consecutive memory blocks in the portable environment address space. Then we pick a random witness block from this memory block spiral. Then we try to create a list of memory blocks that will force the eviction of the witness block. To do that, we pick some random memory blocks, and perform the following measuring routine. We access the witness block, access all the members of the list, and then access the witness block again. But on the second time, we measure the access time to the witness. If the access time is short, we pick more blocks and repeat our measuring routine. We access the witness, access all the members of the list, and then access the witness again. We repeat this process until at some point we have enough memory blocks, so when we access the witness, access all the members of the list, we create a contention. And then when we access the witness again, it was evicted, so it has to be brought back from the main memory to the CPU cache, and this takes a distinguishingly longer amount of time. So at the end of this step, we have a list of memory blocks, some of them corresponding to the same cache set as the witness, and there is enough of them to cause the eviction of the witness, but we have other blocks that correspond to another cache set. So we want to eliminate them. In the next step, we eliminate them by trying to removing them one by one and performing similar measuring routine. We access the witness, access the remaining members of the list, and then access the witness again. If the access time is short, then we remove a member of the list that corresponds to the same cache as the witness, so we need it, and we return it back to our list. However, if we remove another member of the list, and perform this measuring routine, we will see that the access time to the witness is long. The access time to the witness is long. So we remove the unnecessary member of our list. So we'll keep it removed, and we'll proceed with this routine until we remove all the members that does not correspond to the same cache set. The next step, the larger main step of this algorithm, is to collect all the remaining members from the allocated buffer that corresponds to the same cache set as the witness. Which we iterate over all the remaining blocks in the allocated buffer, call them suspect. Then choosing each suspect will perform a similar routine to access the suspect, access the members of the list, and then access the suspect again. If the access time to the suspect is short, then it corresponds to another cache set. And if we chose a suspect that does correspond to the same cache set, then the access time to the suspect will be long, because there was enough memory blocks in our list to cause the eviction of the suspect. So we can perform this routine until we found all the blocks that correspond to the same cache set as the witness, and only them. So now we learn how to build a single eviction set, and we can repeat this procedure by choosing a new witness and repeating steps 2 to 5 again until we mapped all the allocated memory and constructed all the eviction sets. Each eviction set will correspond to its own cache set. So now that we know how to construct eviction sets, we observe that the algorithm has few requirements. It requires a consecutive allocation, and fast and precise memory accesses, and the accurate time source. However, modern browsers try to offer an operating system and hardware agnostic experience. Mainly they offer high-level languages from which the most known and most commonly used is JavaScript. When it comes to cache sidechannel attacks from JavaScript, Oren et al. Demonstrated in 2015 that you can distinguish websites using using cache attack from JavaScript. As a result of the research, browsers reduce the accuracy of the time source available to JavaScript. In the latest versions of the browser, it's too slow. JavaScript is too slow to distinguish between a memory block accessed from the cache and memory block accessed from the main memory. In the meantime, Google developed a portable native client, Pinnacle, for its desktop version of Chrome browser. The main idea of portable native client is to write web applications using low-level languages such as C or C++ and compile them to intermediate binary format. Then, when the user loads the application, it compiles to its native architecture on his own machine by the browser. This allows us to securely execute code at new native execution speed and access system resources directly. Portable native client is available by default in all versions of Chrome desktop browser since 2013. And it actually has all the primitives we need to create the eviction sets. And luckily, in 2017, the W3C group standardized the idea and the concept behind the portable native client to a new standard called WebAssembly, which is now available for all versions of all browsers, including Chrome, Firefox, Edge, practically all of them. And the only implementation difference for us is that we can't access system resources directly. We have to use JavaScript callbacks to access them. So as a result, we can construct eviction sets using Pinnacle. Pinnacle's natively supported contiguous arrays and the clock get time API, which provides a nanosecond accuracy timer, as well as in WebAssembly, where we have the WebAssembly memory object, which is promised to be contiguous, and we can construct a timer using a web worker, where in one context we increment a timer, increment a counter in a tight loop, and in other context we'll access this timer using a shared array buffer, and this will provide us a nanosecond accuracy timer as well. So using those primitives, we were able to construct eviction sets in Pinnacle within a minute inside Chrome browser with up to 2 errors, and using WebAssembly within 11 minutes and up to 8 errors, both in Chrome and Firefox. To demonstrate our attack, we're using an elliptic implementation of Curve 2519 ECDH. So first established notation, elliptic curve differential or ECDH encryption is standardized crypto system. It's standardized by this RFC standard and NE standard. There are a lot of implementations, but we focus on those. Elliptic's implementation JavaScript and Google's end-to-end encryption library. which also implemented in JavaScript. And I'm not going to describe the entire crypto system because we're only interested in this one specific multiplication operation in the decryption, where the secret scalar k from the key setup multiplied by this point received from the ciphertext. To understand how this attack works, we have to understand how elliptic implements the scalar by point multiplication. We put this within point 1, it takes a scalar k in the point p, and returns the multiplication result. Elliptic chose Montgomery ladder multiplication, Montgomery ladder algorithm, which was designed to be more sidechain resistant. And indeed, we see that this algorithm consists of one big loop, where we iterate over the bits of k, and whatever the value of the secret bit I, the secret ith bit of k is, we perform a double and add operation, and it's done add and double, no matter if the value of the ith bit of k is 0 or the ith bit of k is 1. The only difference is the arguments to those functions. So if we try to monitor accesses to the double and add operations, we will see that it's always the same sequence. No matter what the value of the secret key k is, it's always add double, and so on and so on. So another approach that comes to mind is to monitor the accesses to the arguments, A and B. However, since this algorithm is implemented in a high-level language, specifically JavaScript in our case, those variables are reallocated after every iteration. So, the allocation pattern is really random. It's practically impossible to monitor the cache access pattern. So what can we do? As I said, this algorithm is implemented in JavaScript. So it's optimized using the just-in-time compiler on the user inside the user's browser on its own machine. This will result in unpredictable optimizations, unpredictable memory layout, and also unanticipated leakage. So when we executed this code in Google Chrome without any modifications, we observed that when a different access pattern between the case where the secret bit k of k is 0 and the secret bit of k is 1. We were observing different add and double routines access between those cases. It's similar to an optimization pattern of inlining. So using this observation, we were able to extract almost all the secret bits of the key using a single trace of the memory during the decryption, and all the secret bits of the key by just combining 4 traces of the cache activity. We were able to launch this attack by embedding the attacker code in an advertisement and monitoring activity in other tab. We actually published this advertisement using a third-party server, and it still worked. Beside the advertisement attacking scenario, we were able to launch this attack from another browser when our advertisement was running in Firefox and the decryption operations were running in Chrome. So to conclude, we were able to launch a cache sidechain attack from pop under advertisement. We implemented our attack using portable native client and WebAssembly. We attacked JIT code, just-in-time compile code, and not just a single implementation. We demonstrated our attack on multiple implementations of libraries and crypto schemes, and we overcame all the limitations of launching cache sidechain attacks from inside the browser. Thank you. Now I'll take questions.
Thanks for the talk.
Thanks for the talk.
Questions? Remarks?
If I got it right, JavaScript reduced the...
If I got it right, then JavaScript reduced the accuracy of timings, and with Pinnacle and WebAssembly, this is not done because otherwise the applications won't run properly.
Well, for Pinnacle, they just did not reduce the time source. Just another API accessible for Pinnacle. For WebAssembly, they actually does not provide direct access to timer. You have to use JavaScript. So they kind of solved this problem. But we overcame this challenge by using shared array buffer and web workers. Just a second. We used web worker, two web workers. So one of them was implementing a counter, and another thread, another context, was accessing this counter, and this kind of creates a timer with almost the same resolution.
So in the JavaScript you're attacking, did you look at any defense, like changing the Montgomery ladder so that it doesn't do an if, but actually just updates the variables with respect to like the point, like equivalent in C of doing pointer arithmetic? Did you try the defense like that? Because then the JIT wouldn't compile add to two different routines. It would just be the same routine because there's no if statement there.
Well, we can try implementing all kinds of defenses in JavaScript, but it will be very hard to expect what kind of smart thing Google and Mozilla are doing in their JIT optimization engine. They can do all kinds of dynamic optimization, and I think it's like cat and mouse game. The suggestion we offer in our paper is to use the web crypto API provided by JavaScript to do exactly those, to handle exactly those problems, but it's very limited nowadays, and it has to be extended to cover all the primitives we are used to use.
Thanks. Okay, I have a small question. What browser are you running on your machine? I'm going to use the same. Safari is fine?
All of them, it depends on the case.
All versions, alright. Okay.
Like I do the math using a pencil and a paper.
Thank you. Then we will move on to presentation 3 of this session. Right, that's it. This presentation is about the ineffectiveness of internal encodings and about revisiting the DCA attack on white box cryptography, and the presentation is given by Estuardo Alpiles.
Okay, thank you very much. Now we're going to consider a different attack scenario in this presentation. We're going to consider the white box attack scenario, and hereby we're talking about software cryptographic implementations with an embedded secret key on them. And thereby, in the attack scenario, the adversary gets access to the complete implementation code. And he also has the possibility to record different types of information, as in the side channel or in the gray box attack scenario. And he also has the possibility to change intermediate values and perform static analysis. So quite powerful attack capabilities for the adversary. And in white box cryptography, we aim to maintain a cryptographic implementation secure, even when subject to such attack scenarios. So throughout the years, attacks on white box implementations have been presented, and many efficient attacks were based on reverse engineering. And thereby, what the adversary was doing was basically peeling off the software implementation and trying to deobfuscate it until the point that he could extract the embedded secret key hidden on it. And in 2015, and in parallel also in 2016, Bos, Ruben, Michels, and Leuven, and in the other paper, San Felix, Mune, and De Haas presented the differential computation analysis attack. Many of you may have heard of it, and this is a very attractive way of attacking white box implementations, as it can be performed in an automated way, in a very efficient way, and the idea is to analyze or record information during the encryption process from the white box implementation via tooling such as PIN or Valgrind. The information recorded can be such as memory addresses accessed during the encryption process or stack reads and writes. And then this information can be displayed in such a software trace as what we see over here. And what we see here, this is a trace consisting of bit values. This is a sequence of bits. Each sample corresponds to 1 bit. So if you have here, for example, 8 samples, it corresponds to 8 bits. An 8-bit address, for example, and the next 8 bits are it's the next 8-bit address accessed during the encryption process. And in the papers, the authors mentioned or discovered that such software traces could be analyzed using standard DPA tools. And that way, that way they were able to attack many publicly available white box implementations. So it became a very popular approach, and what we were thinking about when we saw the attack, we liked it a lot, but we were wondering why does it actually work, or how is it that standard DPA tools can be used to attack white box implementations. And the question becomes more interesting when we take a look at how white box cryptography is commonly implemented. And in this talk we revisit the DCA attack, and we explain how key dependencies are correlated to the information contained in the software traces, and this leads us to the conclusion that some very popular design frameworks for white box cryptography are not a very safe choice in the light of the DCA attack. So now, how is white box usually implemented, or what are some ways that a white box could be implemented? So in this case we're going to consider AES. So here on the left you see how the AES cipher is implemented, and as you see it consists of these 4 operations and 10 rounds. And in a non-white box implementation we would simply execute each operation after each other and then go to the next round and then do the same. Or we could also do some things in parallel and so on. But at some point we need to read the value of the secret keys, and that's why the idea for a good white box implementation would be to implement this cipher as a very big lookup table that maps directly a plain text to a cipher text. So here in both cases, both programs would give us the same ciphertext for the same plaintext. But of course this is not something very feasible, because we would be talking about a very big lookup table. But the idea of using lookup tables in a way of hiding the secret key, so lookup tables that are dependent or that already have this key dependency on them, this is the idea that remains in popular frameworks for white box cryptography. And what we do is we implement the algorithm steps as a network of lookup tables. So each lookup table corresponds to one step in the algorithm, and hereby the lookup table is dependent of the secret key. As an additional security layer, these lookup tables can be encoded via internal encodings, such that it's not so easy to take a look at the lookup table and then deduce the value of the secret key that this lookup table is dependent of. And the encodings are defined in such a way that they cancel each other out, such that in the end, so for a non-encoded or for an encoded implementation, we will obtain, for each plaintext, we would obtain the same ciphertext, and these are known as internal encodings. So now we take a look at how the differential computation analysis is performed, This may be a bit of a repetition to some of you because it's basically the same as what we do in the differential power analysis attack, but let's just take a look at it quickly. So what we do is we encrypt n plain texts, and thereby by each encryption we record a software trace. So again, a software trace consisting of the memory addresses accessed during the encryption, or stack reads and writes. Then in the second step we define a selection function, and this selection function, what it does is it recalculates an intermediate value of the cipher implemented, and it recalculates it based on the known plain text that we used in the first step and on a key guess. So the hope is that if we use the correct key guess, we will calculate with our selection function exactly the same that has been calculated by the program at a determined point. And the selection function is defined in such a way that it returns only 1 bit of the intermediate state we recalculate. Yeah, I must say that we're talking about here about 8-bit long states, and thereby these states are dependent on an 8-bit fragment of the secret key. Now in step 3 we use the selection function, and for each plain text that we used in step 1 we calculate based on the secret key, and the selection function returns 1 bit of this state. It always returns the same bit. It can be, for example, the most significant bit. And then if for plain text I, our selection function returned a bit value equals to 0, then we group the corresponding software trace in this set A0, and otherwise we group it in set A1. And now in step 4 we calculate the mean value of the sets. We add sample-wise all software traces, and we divide it by the total number of traces in each set. And we do that for both, and then in the end we calculate the difference between both sets. And if we're lucky and we obtain such a software trace, this is the difference of means trace, and it looks familiar from the previous talk. We have peaks over there, and usually in this case peaks mean that we have used the correct key guess. But here we particularly see peak values that are equal to 1. So we have perfect correlations, and when we analyze these results, what happens is, if we take, for example, sample 300, where we have a 1, what happened here is that each trace that we grouped in set A0 had a 0 bit value exactly on that sample, and each trace that we sorted here in A1 had a 1 value, and thereby their mean values were equal to 0 and 1 correspondingly, and the difference was equal to 1. Moreover, this shows us that this white box did not use any encodings. That's why our selection function calculated exactly the same as what the program did. And if you recall, our selection function does not consider any encodings. So we here just how difference of means trace could look in case we use an incorrect key guess. So as you see, our sets consist of, so for the sample 300, they consist of a more or less random selection of zeros and ones, and then the mean values of both sets is more or less equal. So what happens actually when we have intermediate states encoded, which is the usual approach in a white box implementation. And here we have a design framework presented by Chow, Eisen, Johnson, and Van Oorschot. And hereby what they suggested was to, for each key-dependent lookup table, this is commonly known as a T-box in literature, and each output of that lookup table is first encoded via a linear combination or an invertible matrix, and then the output is split into 2, and then each half is encoded by non-linear functions, and then we obtain. So in the end we have one lookup table that maps this input x to this encoded outputs. So these two nibbles over here. So for our analysis, what we did is we first constructed an 8-bit to 8-bit key-dependent lookup table, and we attacked it via the DCA. And then we, for each attack, we always use exactly 256 different inputs, so all possible different inputs. And then we encoded the lookup table using the different encoding, so first using only the linear encodings, and then only using nonlinear encodings, and then using both. And what we wanted to see was how each type of encodings affects the results obtained by the DCA. And then we also constructed complete white boxes, and thereby we consider the same cases, so, sometimes with only one type of encoding, sometimes with both, and then we analyze the results. So here's a summary of the results. In the first row, we have the case that we saw in the previous slides. When we don't use any encodings, we have perfect correlations, and the attack is always successful. When we only use linear encodings, the attack is sometimes successful, but when it is, we have perfect correlations. When we have nonlinear encodings, the attack was almost always successful, so 99% of the time. Thereby, we didn't have we didn't have perfect correlations, but we had such peak values of 0.25, 0.5, 75, or 1. And when we used both, the attack was sometimes successful, and thereby we had the same peak values as over here. And this was the case for when we were using only one lookup table, or when we were attacking a complete white box AES implementation. So for this talk, we're gonna take a look at this case. What happened when we used only a linear encoding. And so our lookup table was constructed this way. So each output of the key-dependent lookup table was encoded by a randomly generated invertible matrix. And then we have a lookup table that maps X to the linearly encoded value M. So when we performed the DCA attack, we obtained such difference of means trace, and that doesn't look very good. We don't have any peak values here, or better said, we have a result equal to, so we have a difference of means value equal to 0, and thereby the DCA has not been successful in this case. So recall that we generated the matrix randomly, and this is what happened here. But what happens, so we were lucky, from a designer point of view, we were lucky because the lookup table was resistant. But since these are generated randomly, there may be some cases where the matrix will not add such an efficient masking. That's, for example, if we consider how each bit of the linearly encoded value is defined. It is defined as a linear combination of the bits in the state C, defined by a row in A. In the case that, so A is the matrix, so in the case that the matrix A, or that row, is an identity row, if it only has one element with value 1 and all others have value 0, then there will be one bit in the state Z that will never be encoded. It will be directly written on the linearly encoded value M. And in that case, when we target that bit with our selection function, we will obtain perfect correlations for the DCA attack. When we randomly constructed a complete white box of AES, that was the case, and we could attack it. Successfully with perfect correlation values. So one may be tempted to think that choosing a matrix that does not have any identity row is a good countermeasure against the DCA attack, since here we saw that the DCA attack was not successful. However, the DCA could be easily modified. We could easily modify our selection function in such a way that after calculating the 8-bit state, we calculate linear combinations of that state, and we sort based on the result obtained from those linear combinations. There will be one linear combination that will be equal to the linear combination defined by some row of the matrix, and that way we will again calculate the same as what the program was calculating, and we will obtain perfect correlations. And now, just to conclude my talk, I just wanted to show you what happened when we attacked a complete white box that made use of both types of encodings. And here in this case, we had these peak values. So again, we have relatively high peaks that let us know that the correct key guess was used, and the attack could be successful. And to say it shortly, what we'll learn here, when we consider the previous case where we only had linear encodings, we learned that if a bit of the state Z can be transformed into any other bit value, so into 0 or 1, then we can expect resistance against the DCA. But if it can only be transformed into one value always, then we don't have resistance against the DCA, which is what happened when we have an identity rule. And for the case that we are attacking a complete white box, or we're designing a complete white box, the matrix A should be able to encode each half of the outputs of the T box in such a way that this 4-bit long value can be transformed into any other 4-bit value. And that way, so that 4-bit value will later be encoded by the nonlinear function, and that way we can expect resistance against the DCA attack. But otherwise, if the matrix is only encoding each half of the output into a subset of a 4-bit long value, then we will not achieve resistance against the DCA attack. And with this, I conclude my talk, and I thank you very much for your attention.
Thanks for the talk.
Thanks for the talk. We have time for questions.
Did you consider bigger encodings, such as 16-bit function?
No, we didn't. So you mean, you mean taking 16-bit long values and then encoding them via...
Yeah, such as the Xiao that is based on this Cho scheme.
No, we didn't have that. But you mean as for the linear encodings?
Yeah, for example.
Yeah. In that case, the results were the same, just that the peaks were somehow spread a bit. They were a bit separated sometimes. But then the actual reason why the attack was successful was because of the nonlinear nibble encodings. Because as Chao had suggested, so the nonlinear encodings are performed nibble-wise and not byte-wise. If we would have byte-wise encodings, not for the nonlinear case, then we would achieve resistance against the DCA.
More questions? Okay, one from my side. The encodings are randomly generated but then fixed, right?
Yeah,
all traces
exactly.
come from the same encoding.
Yeah,
so
exactly.
if I would generate a fresh encoding for every trace,
that would be a good countermeasure. The problem in the white box attack scenario is that this randomness has to come from somewhere, and the adversary may have the chance of turning it off, for example. Okay. Thank you.
okay, thanks again. And then we proceed to the last talk of the session. set. So, last talk is about continuously non-malleable codes with split state refresh. Mark second.
Cool. Thanks for the introduction. So, yeah, as just said, I'm going to speak about this work, which is joint work with Antonio Faunio, Jesper Nielsen, me, and Daniele Venturi. And the talk will basically be split in half of the talk is parsing the title, and half of the talk will be explaining a little bit of what we actually did. So, let's start with non-malleable codes. So these are kind of codes that were introduced in 2010 with kind of cryptographic purpose in mind, and these codes were defined by two procedures, an encoding procedure and a decoding procedure. And kind of you can throw in a message in the encoding procedure, you get a code word, and if you decode the code word, then you get the message back. So this is kind of what they do. And the interesting property that we want from non-malleable codes is that for some kind of adversary A from a class of adversaries here with a fancy A, we want that if we encode the message and then allow the adversary to kind of tamper, somehow change something in the code word, then if we decode this tampered code word, then there are three things that can happen. So the first thing is that, like, even though the adversary changed the code word a little bit, the message that we decode still remains the same. The second case is that the adversary just breaks the code word, so like it's just not decodable anymore at all. Or if he tampers with the message, he can change it to a completely unrelated message, okay? So importantly, the thing that we kind of don't allow here is the adversary cannot take an encoded message and then, let's say, add the value +1. So he can kind of either leave the value the same, break the code word, or like encode a completely unrelated message. So this is kind of the thing that we want. So why would this be useful? Imagine we have some kind of chip, and this chip stores a secret key, which we use to sign messages, okay? And now we want to kind of keep this secret key hidden so that an adversary cannot extract this key. So imagine we just directly store the key on the chip, and now some user can kind of input a message and obtain a signature under the secret key of the message that it gave. What an adversary can do is he can, let's say, do a lot of, let's say, physical attacks on the chip. So he can, I don't know, go swimming with the chip, he can put it in a microwave, he can, like, there are lots of different things that people try, and somehow damage the chip a little bit, or change the value that is on the chip a little bit. So imagine that here he changes the value from SK to some SK star, and this will obviously affect the signing process, because now we're not signing with the original secret key, but with some kind of faulty secret key, or we kind of introduce a fault in the signing process. And it turns out that you can basically leak the whole secret key by just creating one signature, like one faulty signature. This was shown by Bonnet and other people in '97, and yeah, so the important thing is, like, a single faulty signature can leak the whole secret key. So what would we do if we use non-malleable codes? Well, we could say, instead of storing the secret key directly on the chip, we could encode the secret key with a non-malleable code and then just store the encoding of the secret key on the chip. And now whenever we sign, we decode the code word, sign, and output the signature, okay? And now, if an adversary tampers with the code word, we use the properties of the non-malleable code to argue that kind of everything is still okay, because either the code word will decode to the same secret key after it has been tampered with, or the decoded code word will be unrelated. Or, like, I mean, like, the third case is that the code word is just broken, and in this case, just the whole chip and the signing process doesn't work. Okay? So here it's important that the adversary cannot kind of change the message to another related secret key. Okay? So just to give you a little bit of context where non-malleable codes are in the hierarchy of other encoding schemes. So the thing that probably all of you know is error correcting codes. Here we require that if an adversary, or like when we transmit a message on the wire, if there is some error, that the decoding process will obtain the exact message that we encoded. Now, a bit of a weaker requirement is just error detection, which says that either, like, we have the exactly same message, or we detect the error, in which, let's say, we output bottom to signal that there was an error. And non-malleability is weaker than both of those two, because imagine a tampering function which just overrides the code word with like a constant other message. So this would not be a good error detecting code, and this would definitely not be a good error correcting code, but such an adversary would be okay for non-malleable codes. Okay, so non-malleability is a weaker requirement than the two requirements above. So that's a really fantastic primitive, and like if we can have it, then everything is great. The only issue is that we can't have that because that just doesn't exist. So imagine the following. So what I said is that we want this non-malleability to hold for some tampering function or some adversary from like a class of adversaries. So ideally, this class of adversaries is all possible polynomial time adversaries. But now imagine the following adversary. The adversary just decodes the message. There's no secret. You can just do this. He adds +1 and encodes the message. So clearly, this resulting code word is related to the code word he tampered with. And there is no way that we can protect against this with kind of the stuff that I showed you so far about the definition. Yeah, so in research then there are like different ways of how to circumvent these problems, and usually they all involve to kind of restrict the adversary or the class of adversaries that we consider in one or another way. So one of them is we restrict the complexity of the adversary. So for example, you can imagine that we say the adversary is a circuit and the circuit is too small to decode or to encode the code word. So for example, there's this interesting work by Faust et al. About space-bounded adversaries, where kind of the idea is that I'll just make the encoding procedure require a lot of space, and then I say this tampering function doesn't have it, so even though he can decode, he cannot encode the related message. And another way which people use to circumvent this possibility is the split state model, and this is also what we do here. So here you just assume instead of having one code word, you have two code words, and these code words are stored in separate like locations on your hard disk, so to say. And the adversary can tamper with both of them independently, okay? So you can apply a tampering function A0 and you can apply a tampering function A1, but these have to be independent of each other, okay? And it turns out that with this kind of restriction you can achieve a lot of things, and it also is fairly general in the sense that it kind of subsumes a lot of other restrictions that people looked in the literature. Okay. So now we kind of parsed the part of the title where we know what non-malleable codes are and we know what is split state. So the other word we had is continuous. So far when I explained you how the non-malleable codes worked, like I always talk about like you apply one tampering function to the code word and then you see what happens. But in a more realistic setting, if you have such a chip, then you would like to have security even if the adversary can tamper several times with the code word and always see what is the output of the functionality. I won't go into the details of how you define this more formally, but just to give you an idea, so in the real world, the adversary, like you define security here via a simulation paradigm. So what you say is the adversary in the real world, he will tamper with he will submit some tampering function, and then the tampering function will be applied to the code word, and the adversary learns the decoded message of this when I apply the decoding algorithm to the tampered code word. And in the ideal world, I will just have a simulator that obtains the tampering function, and the simulator will basically, without knowing the actual encoding or the actual message, he will simulate the behavior, the view of the adversary. So he will either output, oh, this should decode to the same message, or he will output like to whatever he thinks it should decode. Okay, so continuous means that I allow multiple rounds of tampering, so the adversary cannot submit one tampering function, but like he submits kind of a pair of tampering functions, and based on the output he can adaptively choose another pair of tampering functions, and he can keep doing this, and we still want our non-malleable code to be secure in this case. So this introduces a new problem, which is the so-called fail or not attack. So what happens here is, what I can now do is, imagine I have these two code words, which are somehow bit strings, and now for simplicity assume that if I flip one single bit, this will break the code word, okay? Just to like simplify what the attack is. And what the adversary can now do is he says, okay, I will overwrite the first bit of the last code word to 0. So if the code word was already 0 on that bit, then he changed nothing. If it was 1, then he just broke the code word. And based on the output that he sees, either the message decoded or the code word is broken, he will be able to kind of go through the code word and learn it bit by bit, because we allow several rounds of non-persistent tampering. Okay? So somehow we need to address this, and then there are several ways of how we can do this. One is we say, okay, we will always completely re-encode the whole message. So that means whenever we kind of use what we encoded, we will decode the message, delete it from wherever we stored it on a hard disk, and completely re-encode everything. So this is a bit impractical, people think, so they try to come up with other solutions. So one of them is they say, okay, we will just self-destruct. So this means that you can tamper as long as you want, but if the decoding procedure outputs bottom, so the code word is broken, then they will self-destruct and they don't allow you to perform any more tampering on the code word. And the third option, which was recently introduced by Faunio and Nielsen in 2017, is something called split-state refresh. And here the idea is that I basically have these two separate parts of the code word, and now I design them in such a way that I have a refreshing procedure that I can apply independently and separately to those code words without decoding. So you can imagine that you have kind of your hard disk, and it has two separate locations where the code word is, and then on these separate locations I can apply the refreshing procedure non-interactively without needing to decode the code word first, and without needing to kind of synchronize this refreshing between the two separate code words. Okay? So now we have all the words from the title. Now we can, oh yeah, sorry. So one requirement that is necessary for a code to be continuously non-malleable is that it's hard to find an encoding, two encodings of a message. So let's say one encoding is C0 and C1, and the other encoding is C0 and C1 prime, such that these two encodings share the first part of the encoding, but they decode to different messages. And I will not explain in detail why this doesn't work, but basically you can then, depending on the bits that are in the memory, you can always replace C1 with either the right part of the encoding with either C1 or C1 prime, and then you can again do this kind of leaking of bit by bit information without ever having an invalid code word. So this kind of falls out of the continuous non-malleable codes definition, that this is a necessary requirement for a code to be continuously non-malleable. Okay. So does this work? Oh yeah, cool. So this is basically the work that introduced continuous non-malleable codes, and this work is the work that introduced the refreshing procedure, and all of them are in the split-state model. But the work that introduced continuous non-malleable codes, it doesn't allow for any kind of refreshing as we would like it. And the work of Faunio and Nielsen, it allows us to refresh the code words, but it is not continuously secure. And well, what we do in this work is we construct continuous non-malleable code which allows split-state refresh. And to give you only a very high-level idea of how it works, so we start with the construction of Faunio and Nielsen, which is itself based on a construction of Leuven and Lysianskaya. And the idea is, so I have this line, and everything that is to the left of the line is stored in code word 0, and everything that is stored on the right of the line is stored in code word 1. So what I do is I generate a key pair for a public key encryption scheme, and I store the secret key on the left side, and I store the public key on the right side. And in addition, I store an encryption of the message and a proof, and a non-interactive zero-knowledge proof that says, hey, I know the secret key corresponding to the public key here. Okay? And then they use some kind of, let's say, fancier primitives, which have some nice properties. In particular, the primitives allow you to re-randomize the secret key such that the corresponding public key stays the same. And it allows you to re-randomize the ciphertext such that the encrypted message stays the same, and you can still decrypt it with the same secret key. And also something I will just gloss over, the zero-knowledge proof is also re-randomizable with whatever that means, basically, without going into too much details. And then they say kind of this construction is non-malleable code with refresh, because if you want to refresh, you simply refresh the secret key, the encryption, and the proof. But you don't need to refresh the public key, because even if the adversary, through all of this tampering and the leakage, learns the public key, this is not a useful information, it's a public key. So the problem with this construction is that it's not message unique, because well, I can generate 2 code words for different messages because I can use the same secret key, and here I just encrypt 2 different messages, and then I basically have C0 is the same, but C1 and C1 prime here will be different. So it's not message unique, so this construction cannot be continuously non-malleable. Okay? And what we do is we take this construction and modify it in a way that makes it message unique, and then we show that this is indeed secure. And the modification is actually fairly simple. So what we do is we use an additional commitment scheme which commits to the message M under the randomness R, and we put this commitment on the left side, and in addition we append the randomness here, so also have it on the right side. So now we bind both sides of the encoding to the message, and we bind them both together with the randomness here. And then in addition I use this proof that tells me how I know how to open this commitment, so I know M and R, which are the witnesses here. And even though this seems like a very minor change to the construction, it turns out that we cannot use any of the previous proof techniques, so the proof in the paper is very involved, but I won't go into the details here. Yeah, and now I can, so this is a continuously non-malleable code, and I can refresh it the same way, where I refresh this secret key, I refresh this encryption, and I refresh this proof. And again, like I don't need to refresh the public key, and I don't need to refresh the commitment here, or this proof here, because these are kind of values that even if the adversary knows them, they would leak nothing. And just as a note, the only reason I'm refreshing this is because this is some kind of fancy zero-knowledge proof, which is kind of bound to this encryption. So when I re-randomize this encryption, I need to re-randomize this proof. This is the reason. Okay, so like apart from like maybe being interesting for somebody on its own right, why is this useful? So, for example, there was a paper in 2016 that said that we cannot have non-malleable signatures without the split state model, even if we assume self-destruct. So it's impossible to construct such a primitive. And we show that if you have continuously secure non-malleable codes with refresh, then you can actually build such a primitive. And the other thing that we show is that you can also do something called tamper resilient read-only RAM, where like you have a program and you have some memory, and then you want to encode the memory that you cannot tamper with the memory or with the RAM program. Just to give you an idea of the split state signature scheme, it's ridiculously simple if you have the primitive. So what you do is you take a public and a secret key for a signature scheme, for a regular signature scheme. You encode it into these 2 code words with the non-malleable code that I just explained. You store one half on the one side, the other half of the code word on the other side, and then the signing just works by decoding the code word and signing the message here. And it turns out that if you consider some kind of unforgeability game where, like, in addition to kind of the regular thing that like you can submit a message and obtain a signature, the adversary can also submit a message and tampering functions, and he obtains a signature under the tampered secret key, and he can do this continuously. Then this actually turns out to be a secure signature scheme, assuming that whenever you get a bottom, you refresh the secret key. Okay, do you have questions?